Okay, so as announced, I'm talking about bug class genocide. I've been looking into security vulnerabilities for quite some time now. I started exploiting them, and then in the late 90s it got kind of boring, so I started to look into how to prevent people from exploiting your computer. And that turned out to be actually very hard in practice. We still have a situation where everybody hacks everybody. The NSA hacks the Chinese the NSA hacks Israel, and the Israelis hack the Russians, and of course some of our people hack other people too, but nobody really understands the art of defense, not letting people into your computers. And I'm making a living on security problems and on consulting on how to prevent security issues. And there's a common pattern that you see. There are kinds of bugs that are very, very hard to get right. Like you have to walk through your source code and look at every single line, and every single line has to fulfill a certain property for your software to be good and defensible against certain classes of attacks. Interestingly, you'll find that for certain classes of attacks, for certain classes of vulnerabilities, you can find generic solutions. For instance, for SQL injections, you use prepared statements, right? If I do a code audit, I'm grabbing for all the SQL commands, and if I'm seeing everything is a prepared statement, I don't have to look for any SQL injections anymore. If there's not, if somebody's assembling an SQL statement by hand, that's a problem. Same can be said for quite a number of other classes of vulnerabilities. The one I want to talk about today are buffer overflows, which I assume you to be quite familiar of, so I'm making a virtual process of it. That's essentially the problem. You see, you have some array called sum, and you write into that array, and the input data you get happens to be longer than the 16 characters you see there, and boom, you're overwriting some memory. Now, if you've been paying attention for the last 20 or so congresses and other hacker events, there goes a lot of effort into how to actually exploit things. Because as soon as you write outside that buffer, which is called sum in that case, you tend to overwrite some other data. And from there, you can get into the computer by, for instance, overwriting the return address of a function, very classical Stack Overflow, like in the classical ALF1 paper. Or you could overwrite some structure on the heap, like the doubly linked list that's responsible for memory allocation that gets, the allocator reads a pointer and then writes a pointer and then writes it back. You could write into the structured exception handler on Windows. You can write into quite a number of arbitrary data structures, set jump, long jump buffers. A lot of the things that are under the hood of the C implementation are potentially dangerous, potentially breakable just by writing off your buffer. And so far, well, let's get into more detail. So that kind of problem you see here in that C code, who understands what the problem is here? Raise your hand, please. Good. I'm having a test on that later to see how many of you paid attention. So that's something, we hacker call it a buffer overflow or a heap overflow, and have certain kinds of names for exploits. But it turned out, and that's what I did, that science, actual computer science, the people at university tend to look at the same problems that we hackers do. And they sometimes have their own terminology, but they sometimes also come up with interesting solutions. And one of those interesting solutions I'm going to show to you today. So to get used to the lingo, what we're seeing here is so-called a spatial memory safety problem. Spatial because you're in the wrong part of the address space. You write somewhere you're not supposed to write to. Right? So spatial memory safety. There's also temporal memory safety. That's that. And essentially, you access memory that has been freed, and then you free it again, etc., etc., or you allocate another object and you write into that. Essentially, what happens is that whatever you write to is no longer what you expect it to be. So usually in the case of an allocator, if you call free, then instead of the object, you will have the set of pointers that link the free memory buffers. So freeing them again or mallocating something will chase those pointers and start writing things into your address space. And that usually leads to all sorts of unpleasant situations of overwriting the instruction pointer and giving you code execution one way or another. So that's called temporal memory safety in the lingo of scientists. And the reason why I'm holding that talk is that scientists now have found a solution to that problem that looks like it's viable to use for real-world code. So, as I said, I've worried about that problem for quite a long time. There are a number of existing approaches towards the problem. One that I, if you remember my talks, if you remember what I'm doing, looked very much into is the first point: use a safe language. Don't write in C. So if you, unless you have a very good excuse, C is probably not the right language. Unless you're one of 3 or 4 gurus. One in the room, 2 in the room, third one just got a baby, so not many of you, I trust, writing C code perfectly and correctly. Sorry about that. No offense intended, but it's just the way it is. Most people won't get it right. Then there's the whole topic of mitigations, also something that has been discussed on conferences for quite a while. Use address space layout randomization, use data execution prevention, use stack canaries. And of course, there are ways around that as well. So in case of address space layout randomization, the idea is you might control the instruction pointer by your buffer overflow, but you no longer know where to jump to execute code. Modern exploits use techniques to circumvent that, for instance, finding another vulnerability. So in the old days, you had to find an overflow, a write overrun in memory space. These days, you usually have to find a read vulnerability that gives you read access into the address space of the program you want to attack. Because as soon as you can start reading out parts of memory, you can figure out where things are. So you can circumvent ASLR by reading out the right address. Or you can do what many people do, use heap spraying. It's very popular if you attack a browser. You just have a piece of JavaScript that generates a gazillion copies of your exploit code all over the address space, and essentially you no longer care where you jump to because it will hit your exploit and with a very big likelihood. DEP, data execution prevention. Also in the old days, if you wrote an exploit, you would have that section of memory on the stack, and you would just put the code you execute right into the very same buffer that you overflow. And you would, when then controlling the EIP, the instruction pointer, and the stack frame, you would point it back to the beginning of your buffer, and in that buffer, there are your instructions, and you just execute them. And so some smart people thought, well, we could make the stack non-executable. That will certainly help. Until at that very conference here, people started playing around with what later became known as return-oriented programming. So instead of jumping to your own buffer with code, what you have in your buffer is just a lot of stack frames that actually jump to pre-existing code in the executables. And instead of jumping to your code, you're just looking for a couple of bytes in the program you're attacking that are executable already. You jump there, it executes code, and you're done. You can chain that by chaining stack frames in the buffer you write. So data execution prevention can be worked around. Stack canaries. People thought, I have that buffer, and next to the buffer is my stack frame with the instruction pointer address that I want to control. Well, we put a magic value in here, in between the buffer and my stack frame. And if somebody overwrites the buffer, we'll check whether a certain magic value is still at the right place there. And then if it isn't, we say, oh, we have been attacked. Unfortunately, that's also not 100% secure. Two ways to get around it. First one I already mentioned. If you get read access into the address space, you can find out what the value of the stack canary is and use it. There was a very nice example that FX showed on a Cisco, where you would send an ICMP echo request to a box, which was 20 bytes long. But in the header it says, I'm 1,500 bytes long. And Cisco takes the packet, receives it, sees in the header 1,500 bytes. I'm going to send back 1,500 bytes of my memory. Boom, there you go. Canaries. So stack canaries, they're nice and everything. You can do what Linux did and fuck it up. So for something like the last 6 or 7 years, was fixed half a year ago, when you statically linked an executable, Linux would choose the magic value of 0 for the stack canary. Lots of things that can go wrong there. So, well, Fefe complains that it's just glibc on Linux that does it wrong. Diet-libc gets it right. So a lot of effort has been put into at least give you some decent debugging tools in order to detect memory overruns during production. Most of you probably have heard of Valgrind. It's one of the more popular tools. Essentially, you link a debug version of your program with Valgrind, then run all of your tests, and Valgrind does a lot of things behind the scenes to find out whether you write to memory you're not supposed to write to or not. There have been other ones. The most recent versions of GCC and LLVM ship with something that's called a memory sanitizer that tries to do the same thing. There's the SafeCode project, Secured, SafeC, Cyclone, etc., etc., etc. Some of them are, after-the-fact debugging tools. Some of them actually hook up into your compiler to change things to detect memory flaws. There are, in those approaches, two principal ideas how you detect a buffer overflow, how to detect an invalid memory access. And the first one is the so-called object-based approach. So just for your reference, the notation I'm using here is black is the code that the user actually wrote, and red is the code that was inserted by the tool you're looking at to find your buffer overflow problems. So red is tool injected, black is what the programmer wrote. So the general idea is, in the object-based approach, is that for every object in memory, you know whether that's a valid object or not, which translates into for every address in your address space, you know whether there's a valid object there or not. And all you do is look up whether the address is good or not. So if you look, for instance, at Valgrind, the Valgrind memory profiler, what it does, it keeps a so-called shadow memory. So for every word in memory, they have a data structure somewhere where they store a couple of bits. And those bits are, that's a correctly allocated address, and it's not even been freed yet. So they track whether that's memory that is user visible, as opposed to memory that shouldn't be user visible, like your stack frame or your long jump buffers or whatever. And so they check that and then return whether that's correct or not. So if the byte is broken because it's not user allocated memory that you're looking at, that's bad, an exception is raised. That's all nice and everything until you start looking at examples like that. Because imagine I would allocate a structure like that, then my shadow memory would say, yeah, perfectly fine, everything's allocated memory, and I'm pointing inside the structure here, and I'm not accessing memory that has been freed in between. But still, if I overflow the ID field, I run into the account balance field here. And that's something that, in general, object-based tools do not detect. There are other flaws like that, comparable flaws that it wouldn't detect. Like, for instance, you free a piece of memory, you allocate a different structure, it gets the same address, And suddenly that's valid memory again. And I start writing into memory at an address that's considered valid, even though the actual type of the structure at that place has changed. So Valgrind has a flag for that, so it will not reuse addresses. But in general, that kind of problem make 100% detection of buffer overflows using the object-based approach impossible. So there's an alternative approach, and stuff like secure does it, for instance. And that is, instead of representing a pointer just as a word, you represent the pointer as a word, plus you remember the base, plus you remember the bound. So the base address of the allocated object and the bound of the allocated object. Why you have to do that has to do with the C standard, because you can do pointer arithmetic in C. So you can take a pointer to the beginning of a char array and add 20, and so, suddenly you have a pointer inside that character array, and keep on calculating with that. It's even legal to, add 100, so it points outside, and then subtract 100 again, and then access your memory, because so you might have pointer values that are pointing outside the valid range in intermediate computations and still have it a valid C program. And C programs, unfortunately, actually do that out there. So the fat pointer approach usually involves changing the compiler. And it has the very negative effect of changing the size of your pointer. So your pointer suddenly has all the information it needs to find out whether a memory access is spatially valid if you use the base and the bound address. We're getting to temporal later, just looking at spatial for the moment. Unfortunately, it also means that the layout of your structures change. So it breaks compatibility with the existing C program. So if you look at the existing solutions that use fat pointers, they usually suffer from a number of problems. One is incompatibility by breaking your structure offsets and everything, so memory layout changes. Calling conventions change, so you cannot link against uninstrumented libraries. You cannot do separate compilation. It usually involves things like a whole program analysis pass, where instead of compiling a list of object files, you take all your source code, all your millions of lines of C, and compile them all at the same time. You can do interesting things then, but it turns out to be not very practical if you actually try to compile real-world software with it. So both approaches have their drawbacks and their advantages. So enter soft-bound CTS. So one noticeable thing about academia, they get naming of software even worse than hackers do. It's called soft-bound CTS, soft-bound because they had a hard-bound project before, where they researched hardware support for checking every pointer access for bounds violations, and soft-bound was the implementation of the same algorithm in software. And CTS talks about compiler-enhanced temporal safety. So we got that abbreviation. That's research that has been done at University of Pennsylvania. The soft-bound part does your spatial safety, whether we overrun some piece of memory in the spatial domain, wrong address. And CETS is the part that does the temporal safety, meaning accessing memory that has been freed, essentially, or not yet allocated. The thing that makes it interesting here is that they managed to get something that's reasonable for actual use out there. If you have ever used Valgrind, it slows down your program by a factor of 20. That's nice and everything for testing. You can do that during testing and debugging. You wouldn't want to ship something linked with Valgrind to a user. It uses disjoint fat pointers. You remember object-based versus pointer-based? So what it does to remove many of the incompatibility problems that exist with the fat pointer-based approach is that they have shadow memory, as they would have in an object-based approach, but they're only using that to store the additional pointer information. So the memory structures keep the same, stack frames keep the same, but the extra information you need is propagated on a different way. I'm getting into the details how they're doing that later. they have a proof of correctness of what they're doing, and that's very interesting. So they have a formal representation of the semantics of a subset of C, and they prove that with that transformation, no invalid access of memory can be written down without being detected. That proof has a certain problem. I'm coming back to that later, but that's already very remarkable. And it's implemented, and that's another point of why it generates very efficient code. It's implemented as an LLVM optimizer pass. So it operates on LLVM intermediate representation, which is so-called single static assignment. So no idea how many people of you ever looked into computer intermediates. It's sort of above assembler level, but below C level. And you can get that essentially by breaking down your code and taking all the big expressions. And for every sub-expression that you write down, so if you write A plus B plus C, so D equals A plus B plus C, you say my temporary T1 is A plus B, and my temporary T2 is T1 plus C. So you break down compound expressions into simple expressions. And you also do not reuse variables. You only use variables once, you assign to them, and then never change them. And the intermediate representation in LLVM is typed. So unlike, for instance, Valgrind, which just looks at the assembler level, at memory loads and stores, if we compile a program and we look at an intermediate stage, we still know what variables we access are pointers and which are integers. And so we can drop a lot of the load and store checks and only look at those checks which are actually relevant to the program. So that sounded on paper like a very promising project, and I started looking into it. Yeah, so the advantages you get is source compatibility. Some of the competing projects, you had to start modifying your C code in order to get it to compile with the tool. It gets complete coverage. It actually gets 100% of your memory safety problems and catches them. It supports separate compilation, so you can compile a library and link it against your main executable like you're used to, instead of having to compile all your C code at once. And it's got a low overhead. So at the end, something like 100%. It makes your code half as fast as it used to be. But, you know, that sounds like much. You know, if you're a C programmer and somebody says, like, I have that optimization that makes your program 3% faster, you go, wow. Then you come and say, well, and now I make it half as fast. You go, what? But then you remember that people actually use Ruby to serve web pages out there. So I can imagine quite a lot of applications where a 100% performance overhead is really, really cheap compared to getting pwned by the NSA or somebody. So I thought it was a worthwhile project. So what are they doing? Essentially, again, black is what the user writes, red is what the tool is inserting. We're looking at C code here, which we have to think about as a high-level representation of the intermediate representation it's actually working on. And we see there, that's a load from a pointer there. The check for a store would be totally equivalent. And all it does is go through the intermediate representation of your code. And for every pointer access, it inserts a check for the pointer, whether the base and the bound are in the right range. It involves the axis, the size of the axis type, because it might be the case that your pointer is, you know, just pointing to the end of the structure, but still inside. But if you read the whole word, then a few bytes will spill over. And yeah, 1 byte of buffer overflow are sufficient. I've seen a presentation also at CCC Congress, where an exploit was written for a 1 byte overflow, because that 1 byte overflow flew in right to the base pointer. So one could create a copy of the stack frame a few bytes off inside the buffer and then point off of that. So the size of the thing still plays a role. The implementation of that check is pretty straightforward. Okay. Fif has been laughing. Do I hear more laughs? Who's laughing? If you're not laughing, I'm not trusting your C code. If you don't see that, you're not supposed to write security critical C code. Because, you know, they have their formal proof of correctness of their algorithm and everything, but then they insert all the right checks to find 100% of the buffer overflows, but then they get the check wrong. What's wrong with that check? You know? The addition of pointer plus size might overflow. So you have to check for that. I wrote to the authors and they said, yeah, you know, that's academic research we're doing here, and it's nice that somebody looks at actual. But other than that, it's a fine piece of software. So the research part they're doing is quite good, and I think we should do more projects where hackers look into research out there and try to liberate it into real-world existing open-source software, for instance. The base and the bound value, they have to come from somewhere. That's the fat pointer I talked about. So we need to calculate them on memory allocation. So in the case of malloc, now the pointer address is the base, and the bound is the pointer address plus the size that was requested to malloc. And you know, if malloc returns null, then of course our bound is also null. If you have a null pointer gets a 0 size in the internal representation, so the check fails because the memory access will always override the 0 sized buffer. So very easy here. Stack allocation pretty much works the same. Base address is the base address of the array, and the bound is the base plus the size of the array. Very, very straightforward. This is where C is tricky, and this is why it's hard to come up with a good memory access solution for C. You have pointer arithmetic. Essentially what you do, if your new pointer is a pointer plus an index, the new pointer copies the base address of the original pointer, and it copies the bound address of the original pointer. You will notice that inside that representation, the pointer might point outside the object temporarily, but every time we do pointer arithmetic, it's recomputed, so after the next add, we might be back into the array and everything is fine. Here's a special case. And that's the case I've talked about, that you get the address of a member of a structure and access that. And essentially what you do is you narrow your bounds to that member of that structure. You might end up with a couple of false positives there, because you know, somebody might think it's smart to, you know, when writing a program that deals with 3D graphics, have a struct that has an X, a Y, and a Z as members. And then the whole struct is passed to some other function that interprets the very same structure as an array of floats instead of a struct of float with 3 members, because the memory representation is the same. It's something we cannot tell apart here. So this will prevent overruns inside a structure. It will prevent certain kinds of dirty hacks in your C program if you decide to do them. So something we can live with. Another case of narrowing is when you access an array inside the structure instead of just an int, but it boils down to the same principle. This is where it gets interesting. We know that our pointers now have 3 values. It's the pointer value, it's the base, and the bound. And we also know that we do not want to change representation of structures in memory. So if we have an object in memory and we load a pointer from that address, we have to get our base and our bound from somewhere. So opposed to the other fat pointer implementations, softbound CTS uses a shadow space, a data structure that keeps the copies around. So essentially what that does is a table lookup based on the pointer and returning the base and bound address. There's something tricky here. You might not see that immediately. We do not use the pointer value for the lookup of the base and the bound. We use the address of the pointer in memory. Notice the 2 stars up there. We're using the address of the pointer in memory to get an index into our table to get the additional information. So instead of coupling something to the pointer value, we copy some additional information to the variable location at the end of the day that we use to keep the base bound around. So, of course, inside the function, that's just passed in additional registers. So there are local variables that are generated during translation of a function for the base and the bound if there's a pointer. And this only applies when actually loading something from memory as opposed to getting a value that was an intermediate result of computation inside your function or something that was passed as a parameter. Storing metadata works the same whenever we write to a memory location that is a pointer. And we know it's a pointer because we're working on a timed intermediate representation in the compiler. Then we have to do that additional store. There are certain alternatives for the implementation of that store. So the thing abstracted behind the table look up there. We could implement it as a hash table. As you can imagine, that's a very expensive operation to look into a hash table or write into a hash table every time you write or read a pointer from or to memory. You could use an actual shadow space. So when you have a heap of, say, size 16 megabyte, you allocate another 16 megabyte for your base addresses, another 16 megabyte for your bound addresses. And then it's a very simple operation, right? You do an XOR with your pointer address and you suddenly get the address of the base and the bound value. That's very fast, but it needs a lot of memory. And it turned out that after quite a lot of experimentation that the optimum data structure for that is a tree that's written T-R-I-E. Some people call it tray or pronounce it tray. Some people call it a radix tree. At the end of the day, it works like a page table system. So you take a certain number of bits from a pointer address, and that points you to a secondary table that is just a page of values. And that turns out to be sufficiently memory efficient to not be a problem, but also fast to access, because all you have to do is XOR the right things, shift things around, do a pointer lookup, and you get your table value. What it does, however, with the performance is that it introduces additional loads and stores. So from a performance point of view, you might think that the actual computation for checking the bounds is what makes the program slow, and that's absolutely totally not the case. If you think that, you haven't looked into modern CPU architectures. In a modern computer, the access time to memory dominates everything that you do on a CPU. So it's not unusual to have a 180 cycle round trip for just loading a word from RAM if it's not in cache, and all the while twiddling your thumbs. Also, you have a superscalar execution on modern CPUs, and the kind of check that's introduced for the bounds check is something that's very, very easily parallelizable. So it increases the parallelism of your software. It's more instructions that can be run at the same time. So your actual check can be distributed onto different instruction units inside your CPU. So that tends to take almost no time at all. The actual overhead you're paying is for the extra loads and stores that are done to memory here for the structure access. And that's what the overhead comes from, your 100% overhead. In order to prevent loading and storing from those, whatever it is, hash table, radix tree, shadow memory, all of the time, an additional modification that softbound does is modifying the calling convention. So this here is an illustration. Think about it of a Serviervorschlag. It doesn't work like that internally. What it internally does is it keeps a so-called shadow stack for the additional base and bound values. So if I pass in one pointer, like the s and that function there, an additional s base and s bound is passed into the function body. Actually, that resides on a different stack from the main stack. So in order not to mess up stack layout and everything that's involved in there, and to improve compatibility. But yeah, so we augment that. So usually the additional information, the base and bound information, are passed around like additional function parameters. They're passed around inside registers, inside the functions. And actual load and store from and to memory only happens if we update our heap objects. Yeah, there are a couple of loose ends, things that need to be treated here. Global variables. For global variables, there's a path that hooks into the program load and using the .init section in ELF, and that generates the base and bound information for all the globals, so they can be accessible. Separate compilation is supported by defining an ABI to call through that. Memcopy is interesting, because if you do memcopy of memory region A to memory region B, inside that memory there might be pointers, and the pointer meta information, the base and bound, also needs to be copied. So you need to have a special memcopy implementation that makes sure that the additional base and bound information is also copied around. Function pointers are interesting. Function pointers just get a bound of 0, so you cannot write into them, and then they're safe. Casting is a problem. If you have an integer and you create a pointer from it, at that point in time, the C compiler has completely lost track about the original type of the data that went into there. So essentially, there's nothing sensible you can do there to prevent buffer overflows. So what softbound does is, if you cast an integer to a pointer, it gets a bound of 0, so you cannot write to that memory access. So it completely prevents you from using integers as pointers. That kills a couple of hacks. Some people of you might know the trick of using XOR to XOR two pointers onto each other to generate a doubly linked list with only one pointer field. That doesn't work if you have that limitation. But such code is rare, fortunately, and you can't touch the 3 lines that do that. Casts and unions, they just need to be treated right. Like at the moment where you access that memory, the conversion has to be applied. That works. And the one thing that's still a bit unsolved here is var args. So that's where the truth is. They're not reaching 100% yet. Var args are not treated yet because they're special. You would need to add a base and a bound information to the array containing your var args. That's not there yet. It needs to be implemented. So 97% format string exploits are not covered yet. Okay, on to temporal allocation. That's a bit quicker now because you already know the principle of passing fat pointers around. What we do for temporal is that we have 2 additional fields in our fat pointer. One is a key and one is a log. The log is an address in memory, and the key is a value we increment every time you say malloc. So we know it's memory allocation 23. And then we have an association between a pointer and the log. At the moment where free is called, the memory that holds the log is reset to 0. I hope that will get obvious in the next slide. So that's the check that's introduced there. I get the key and the log address as part of my fat pointer implementation in shadow space. And I load from the log address, and if that's what at the log address matches my key value, then I didn't call free on that pointer yet. At the moment where I call free, where's free? Here's free. At the moment where I call free, all I do is go to my log address and write invalid log at that address. So yeah, as long as the key fits the log, my pointer is valid. So for every allocation, I remember the correct log value. And then propagation of metadata pretty much works again like the spatial checks. You've seen that all. Loads and stores. Globals cannot be freed, so we just introduce a key which is a global key and a global log address that always match to each other, so when a global is accessed, we have a key and a log that work. Yeah, and that will be all nice and fine unless we wouldn't have threads. Unfortunately, we do. So that's again where we don't reach the 100% yet. If you have shared state, if you have threads, if you have shared memory, it might happen that one thread calls free and the other one checks whether the log is still valid, and you have the process switch in between. So one process sees, yeah, the log is still valid, Then the other one gets scheduled, does the free, kills the lock, and then you're getting back to the first thread, which then accesses uninitialized memory, and we do not want to have that. So, own contribution. I'm not just telling you what people out there did, I actually did my own hacking on that. At the moment, the form of softbound CTS you're getting is a collection of patches to LLVM with their own top-level executable, and all that does is processing LLVM intermediate representation. And it also has a number of other nasty hacks, like in the compiler module, it keeps a list of libc functions, and then for every function inside libc, it comes with its own wrapper function that need to be wrapped when you want to call in there. And I started around hacking with that, and it turned out to be intractable. You discover interesting things when you do that, like, for instance, that in the Linux headers, they call different functions depending on whether you enable the optimizer or not. They actually have an if-def, did the user use optimization inside that function or not, then use one function, else use the other function. And you end up with a ton of libc internal functions that you need to wrap and then recompile the compiler and work on your code, and that all led to nowhere. So I found out that FreeBSD actually is compilable using LLVM, and chose that as a target for further hacking. And what I did, with a lot of support from Hannes Mehnert, who hacked on that with me, he was the FreeBSD domain expert and also coffee guru. Check out his coffee on the fourth floor, he's good. I can compile the whole userland using LLVM from scratch with every single line of code, and that's a nice support to actually start hacking on that stuff. So what I did was introduce function attributes that you can specify that turn on or turn off the softbound CTS processing for a function. The other one is, so one is for saying, that's a native function like is this call, don't do anything, it's just a C function. The other one is like, that's a string copy function, and you might want to give me your base and bound for the strings you pass, but I want to write the check myself in order not to check every single byte in the loop for high performance. That's the other attribute. We ported the softbound CTS module to FreeBSD, which essentially involved a lot of hackery with the build system in order to get the additional modules built. And then we had to walk through the startup. So everything that happens between _start, which is your ELF symbol entry into the executable binary, up until main, which is your main entry as a C programmer. A lot of things happen there. Like, for instance, all the constructors are called, thread local storage is initialized, malloc is initialized, and that's all low-level code. So as you have seen, malloc and free are essentially primitives, and you have wrappers around there that provide the correct base, bound, lock, and key values. So we had to go through that and find every single function that's involved in program startup, annotate that with the right attribute, come up with a malloc that does the right thing, wrap the malloc to give back the fat pointer values. And then we could delete about 2,000 lines of code in the softbound CTS because it was no longer needed, yay. Yeah, and actually we're at the point at the moment where a Hello World executable can be built and executed and will correctly load, come up to main, and then I have a little test function that overrides a buffer, and it correctly detects the overflow if the overflow happens, and then the executable is shut down correctly again. So I would call that a proof of concept. It's a little bit better than the academic code from a usability perspective, not much from an industrial strength perspective, but I think it's a very promising approach to that. So next steps in that will be making that clean, making sure all the functions are instrumented and work, and then start doing tests, fix some things like inlining, for instance, so that the buffer overflow check you've seen is not inlined due to the way it works. And I think we can get a lot of performance wins from there by inlining stuff. And the goal of that operation is to have a complete FreeBSD world where every single line of code, except for a little bit of trusted code, which is essentially malloc and the libc startup, is correctly, spatially, and temporally bounce checked. Because it would be really nice to have a computer for a change that's not vulnerable to buffer overflows, because I didn't have any for the last 20 years. Go through all the vendors, nobody gets it right. So that's links to the original source and to the GitHub with our modifications. I would like to thank Hannes Mehnert again for hacking that code with me. Would like to thank the original softbound CTS authors for being very generous with information. One tip they gave me, the spatial memory checking, they talked to Intel, and Intel is working on a CPU set extension, so we will get native instructions that do the bounds checking for us later. It's called the NPX extension, watch out for that. And generally for coming up with some awesome research. Yeah, so thanks to you for listening, and I'm open for questions now.
Hello.
Yeah.
Did you know that set pointers is not an invention of the people of the softbound set CTS project? It is a word from the dark time of C-programming on 80x86 times, when they had this model, the same model of the register, which you have to load with a 64K module.
Yeah, yeah.
So this is exactly the boring model of C programming, where no Unix programming was able to compile on Unix, on MS-DOS.
Sorry if I raised the idea that softbound invented that. Of course, fat pointers are old. They're even older than that. 60s hardware had it. Like you had bounds checked pointer accesses in hardware even in the 60s. So it's nothing new. It's just that that particular hack allows us to run real-world existing C code on real-world hardware these days. So I think that's what makes it unique.